What if one of the biggest inefficiencies in modern LM is that they are forced to compute things they should simply remember? That is exactly the question DeepSeek's latest paper tries to answer, and the answer reshapes how we think about scaling models. The field of artificial intelligence is increasingly focused on separating reasoning capabilities from factual memory. Karpathy discusses exactly this idea in the following talk.
If they had less knowledge or less memory,
Yeah.
actually maybe they would be better.
Yeah.
And so what I think we have to do kind of going forward, and this would be part of the research paradigms, is I actually think we need to start, we need to figure out ways to remove some of the knowledge and to keep what I call this as this cognitive core. So that's why when I talk about the cognitive core, I actually want to remove the memory, which is what we talked about. I'd love to have them have less memory so that they have to look things up.
The core intuition is that if we can build a model that does not store factual knowledge but instead specializes in reasoning, we can attach a retrieval system to it and obtain a small, efficient model with strong capabilities and an almost unbounded memory that is limited mainly by retrieval. This week, DeepSeek AI made a concrete move in that direction with a paper called Engram, Conditional Memory via Scalable Lookup, a new axis of sparsity for large language models. Modern LMs are remarkably good at reasoning, but they are also remarkably wasteful at remembering simple things. When a transformer sees a phrase like Diana, Princess of Wales, it does not retrieve that entity. It reconstructs its meaning, layer by layer, through attention and feed-forward networks. That reconstruction consumes depth, attention capacity, and compute, even though the information itself is static and was seen thousands of times in training. The reason is simple. Transformers have no native lookup operation. They only know how to transform vectors. So they are forced to simulate memory using computation, and that simulation runs on every token, in every layer for every query. Even mixture of experts does not fix this. MOE scales computation via conditional routing, but it still asks the network to reconstruct static facts through activations. A key insight in the paper is that language modeling is not one monolithic task. It is actually two very different workloads glued together. Dynamic reasoning, logical composition, multi-step inference, math, code generation. Genuinely hard, genuinely adaptive. Static pattern recall, named entities, idioms, grammatical templates, common phrases, short code snippets. Local, repetitive, context invariant. Transformers treat both the same way. Engram argues they should not. MOE handles thinking. Engram handles remembering. This is the new axis of sparsity the paper introduces. Conditional computation via MOE and conditional memory via Engram are two independent tools. And the paper shows that using both together is strictly better than using only one. Engram is a module embedded inside the transformer. It is parametric, trained end-to-end, and fully differentiable. Conceptually, it behaves like a modernized Engram memory table. First, at each token position, the model looks at the local suffix context, typically 2 grams and 3 grams. These short windows are ideal for capturing entities, phrases, and syntactic templates. Second, tokens are normalized through a compression step that collapses superficial differences like casing, whitespace, and Unicode variants. This gives a denser, more efficient memory space with fewer wasted slots. Third, the normalized n-grams are passed through multiple hash functions, each deterministically mapping the n-gram to a slot in a large embedding table. Multiple hash heads reduce collision noise. Fourth, the retrieved vectors are concatenated into a memory vector, lightly processed by a small causal convolution, and added back to the hidden state via a residual connection. What is important to note? The memory is query-independent and deterministically addressed. Unlike attention, the retrieval is constant time, O of 1 per token. It is independent of sequence length, and it is deterministic. The same n-gram always hits the same slots. And unlike RAG, this is not external retrieval over documents. Engram is part of the model itself, learned alongside the rest of the weights. Raw static memory is dangerous. A lookup can be ambiguous, ridiculous in context, or just wrong. A naive implementation would inject noise into the hidden state and hurt performance. Engram solves this with a context-aware gate, which plays a role closely analogous to cross-attention. The current hidden state acts as a query that decides how much of the retrieved memory should be trusted. If the memory aligns with the current context, the gate opens and memory contributes strongly. If the memory conflicts with what the model is reasoning about, the gate suppresses it almost completely. So relevance is not determined at retrieval time. It is determined by this fusion module after retrieval, which is why a static, deterministic lookup table can still behave in a context-sensitive way. This single design choice is what makes Engram robust enough to help not just factual recall, but reasoning-heavy tasks too. One of the most important contributions of the paper is what DeepSeek calls the Sparsity Allocation Law. Given a fixed parameter budget and fixed FLOPs, how should you split sparse capacity between MOE experts for computation and Engram embeddings for memory? The result is a clear U-shaped curve. Pure MOE is not optimal. Pure memory is obviously not optimal either. The best configurations allocate roughly 20 to 25% of sparse parameters to memory and the remaining 75 to 80% to MOE. That finding is more interesting than it sounds. It means memory is not a nice-to-have add-on. It is a first-class scaling dimension, sitting alongside computation, and you leave performance on the table if you ignore it. Why do reasoning, math, and long context all improve? You might expect Engram to help only factual benchmarks like MMLU. And it does. The 27 billion parameter Engram model beats an ISO parameter, ISO-FLOPS MOE baseline by plus 3.4 on MMLU and plus 4.0 on CMMLU. But the bigger surprises are elsewhere. BBH plus 5.0, AR challenge plus 3.7, human eval plus 3.0, math plus 2.4, multi-query needle in a haystack 84.2 to 97.0. Why would a memory module help reasoning and math? The mechanistic analysis in the paper gives a beautifully simple answer. By offloading local, static reconstruction to the memory table, the early transformer layers finish their easy work much faster. Early layers in Engram models start behaving like much deeper layers in MOE-only models. The model reaches prediction-ready representation sooner, which effectively deepens the usable network for complex reasoning. And because local dependencies are handled by lookups, attention is freed to focus on global structure. That is why long context retrieval jumps so dramatically. Engram does not make models smarter by stuffing them with more facts. It makes them smarter by freeing compute. There is one more advantage that may be the most important for the future of large models. Because Engram's memory indices depend only on input tokens, not on activations, lookups are deterministic and predictable ahead of time. That enables asynchronous prefetching from host memory or SSD, communication computation overlap with the GPU's forward pass, and offloading massive memory tables to CPU without sacrificing throughput. DeepSeek shows that even a 100 billion parameter memory table can be offloaded to host memory with less than 3% inference overhead. That changes the economics of scale. GPU HBM is the single most expensive resource in modern AI infrastructure. If you can grow capacity by adding cheap CPU memory and keep the GPU busy with reasoning rather than retrieval, the cost curve for smarter models flattens significantly. Has DeepSeek actually solved the separation of reasoning and memory? It is too early to say, and only real-world deployments and whatever ships in DeepSeek v4 will really answer that. But the direction is unmistakable. Engram introduces conditional memory as a first-class architectural primitive alongside conditional computation. Together they complete the sparsity story. Think with computation. Remember with memory. Scale both independently. Transformers have been forced to compute when they should have remembered. Engram finally gives them memory, and in doing so, it makes reasoning cheaper, deeper, and more scalable. If you made it this far, you are clearly the kind of person who likes thinking about how these models actually work under the hood, and that is exactly who this channel is for. If this video helped the ideas click, a quick like genuinely helps the algorithm share it with more curious minds, and subscribing means you will catch the next paper breakdown the moment it drops. I would love to hear your take in the comments. Do you think conditional memory is the missing piece? Or is this just another clever trick that will fade once the next architecture arrives? Let me know. Thanks for watching, and I will see you in the next one.